All right, I want you to imagine a material that, logically speaking, really shouldn't even exist. Picture something that is almost as hard as a diamond, yet possesses the sheer brute force toughness to literally chew through solid rock without shattering. I know, it sounds exactly like science fiction, right? Well, it's not. To really appreciate how wild this is, we've got to look at the ultimate trade-off in materials science. You see, materials are almost always divided into two distinct camps. On one side, you have ceramics, like glass or diamond. They have extreme hardness, but they are highly brittle. Drop them, and they shatter. On the other side, you have metals, like copper. They have incredible toughness to resist cracking under impact, but they're incredibly soft. For centuries, engineers were forced to choose one or the other. But what if you could actually hack that rule? Well, welcome to this explainer on tungsten carbide, the ultimate industrial shapeshifter. This right here is the unsung hero of modern manufacturing, an engineered composite that successfully bridges that impossible gap between hard ceramics and tough metals. Here is our roadmap for today. We're going to cover the ultimate industrial paradox, the tungsten carbide recipe, the magic of sintering, modern manufacturing bottlenecks, and finally, 3D printing and beyond. Part 1. The ultimate industrial paradox. So, to make sense of this paradox, let's jump back to 1893. French chemist Henri Moissan was trying to make synthetic diamonds. Actually, scratch that. He was trying to use a massive electric arc furnace to force carbon to crystallize. But instead, he accidentally synthesized tungsten carbide. Now, Moissan's creation was exceptionally hard, practically approaching diamond on the Mohs scale. But there was a massive catch. It was plagued by extreme brittleness and porosity. You just couldn't form it into solid, usable engineering shapes. So for the next 3 decades, this incredible substance just sat on a shelf as a totally useless, highly brittle laboratory curiosity.
Part 2. The tungsten carbide recipe.
So how exactly did we get from a brittle lab curiosity to a global industrial staple? The breakthrough finally happened in the 1920s at Germany's Osram Lamp Works. They desperately needed a cheaper, more durable alternative to the diamond dyes they were using to draw electric lamp filaments, and their engineers completely cracked the code. They realized that pure tungsten carbide was just too brittle on its own, so they engineered a composite. Think of it using the analogy of a brick wall. They used tungsten carbide grains as the hard bricks, and then they added a small amount of a ductile metal, specifically cobalt, to act as the mortar. By binding these incredibly hard ceramic bricks together with a tough, shock-absorbing metallic mortar, they created the very first viable cemented carbide.
Now, like any great recipe, the devil is totally in the details. Carbon sources, like graphite or carbon black, are used to form the carbide itself. So the absolute crucial point here is that this requires razor-thin process control. If your carbon ratio is even slightly off, the whole thing fails. Too much carbon, and you get these weak graphite pockets. Too little carbon, and you form a highly brittle secondary phase that completely ruins the tool's toughness.
And it doesn't stop there. To get that absolute perfect structure, engineers throw in something called grain growth inhibitors. Minor chemical additions, like vanadium carbide or chromium carbide, are mixed directly into the powder. Why does this matter? Well, during processing, these inhibitors literally pin the grain boundaries in place. They act like microscopic traffic cops, stopping the tungsten carbide grains from clumping together and growing too large, which would severely degrade the material's final hardness.
Part 3. The magic of sintering.
So you might be wondering, how do we actually take this loose, dusty powder and turn it into a dense, rock-crushing composite? First, the powders are milled and mixed into a perfectly uniform slurry. Then they're compacted under immense pressure into what the industry calls a green body. This is a soft, chalky, porous preform that holds the rough shape of the final part. But the real magic happens in step 3, liquid phase sintering, when that fragile green body goes into a controlled atmosphere furnace. Inside the furnace, the temperature ramps up to a staggering 1400 degrees Celsius. To put that into perspective, that is insanely hot. At this extreme heat, the cobalt binder completely melts into a liquid. It wets the hard tungsten carbide grains, and through sheer capillary action, it pulls them together. The smaller grains dissolve into the molten cobalt and then reprecipitate onto the larger ones. When the part finally cools, you are left with a composite that is over 99.9% dense. All that open porosity, completely gone. It is just a stunning metallurgical transformation. And today, researchers are pushing things way further with techniques like spark plasma sintering, or SPS.
Instead of sitting in a conventional furnace for hours on end, SPS uses mechanical pressure combined with a pulsed direct current that shoots right through the powder compact. It generates internal Joule heat so incredibly fast that the entire sintering cycle takes just minutes. This rapid process densifies nanostructured powders before the grains even have time to grow, locking in those ultrafine, super hard microstructures. Moving on to part 4, modern manufacturing bottlenecks. Here's the thing, that traditional recipe that served heavy industry for a century, it's suddenly hitting a massive wall. The industry is currently facing a huge crisis around cobalt. While it's an incredible metallic binder, cobalt is toxic. It's actually classified as a carcinogen under EU REACH regulations. It's also politically fraught, with heavily concentrated global supply chains causing crazy price volatility. On top of that, cobalt corrodes in highly acidic or high-temperature environments, and mechanically, traditional die pressing simply cannot create the complex internal geometries that modern high-tech engineering demands. We desperately need a 21st century upgrade. Which brings us to part 5, 3D printing and beyond. To ditch that toxic cobalt, scientists are developing high-entropy alloys, or HEAs. Instead of relying on just one principal metal, HEAs combine 5 or more metallic elements in roughly equal amounts. This creates this really complex, distorted atomic lattice that results in what they call sluggish diffusion. It naturally suppresses grain growth during sintering, while dramatically improving the material's resistance to extreme heat and corrosion. It's a real game changer. And to solve that geometry problem we talked about, we are looking straight to additive manufacturing. Yep, 3D printing. Conventional pressing is fantastic if you want high volumes, simple shapes with uniform density, but additive manufacturing throws the entire rulebook out the window. We are talking about printing custom cutting tools with intricate internal cooling channels or complex wear parts that would be literally impossible to press in a traditional mold. But listen, 3D printing tungsten carbide, it is not easy. Methods like binder jetting, where liquid binder is printed selectively right onto powder layers, are showing massive promise. But processes like laser powder bed fusion are currently battling severe thermal gradients. The melting points between the carbide and the binder are just so vastly different that thermal cracking and elemental evaporation are huge hurdles. Overcoming this cracking is absolutely the bleeding edge of current materials research. So how do we actually fix this? Well, we take the whole shebang into the digital realm. Researchers are shifting away from expensive, trial-and-error physical experiments and are instead using predictive modeling and digital twins. By simulating atomic interactions and thermal stresses inside a computer, they can perfectly optimize the 3D printing parameters before a single laser is ever fired. This drastically enhances both the material's performance and the overall sustainability of the process. And speaking of sustainability, here is something you absolutely need to take away from this explainer. Today, up to 40% of global tungsten carbide production comes directly from recycled scrap. Using advanced techniques like the zinc melt process, we can actually dissolve the binder, safely recover the original carbide grains, and close the loop on this critical material. This significantly reduces our reliance on precarious global mining. Which brings us to a final provocative thought to leave you with. We started with Henri Moissan accidentally creating a brittle, useless rock back in 1893. Today, we're modeling it with AI, we're binding it with high-entropy alloys, 3D printing it into impossible shapes, and recycling it to save the planet. So how will 21st century technology continue to reshape this incredible material? The paradox of hardness and toughness has been solved for sure, but the evolution of tungsten carbide is clearly just beginning. Thanks so much for joining me on this explainer. I hope this sparked your curiosity as much as it did mine.